Quantum reality reveals a universe where particles exist in multiple states simultaneously. Distant objects influence each other instantaneously, and the act of observation fundamentally alters what we measure. A discovery so profoundly unsettling that even after a century, scientists cannot agree on what it actually means about the nature of existence itself. A particle exists in two places at once until you look at it. Then reality decides which location is real. And here's the terrifying part. Scientists with decades of experience studying quantum mechanics cannot agree on whether this means reality doesn't exist until we observe it, whether infinite parallel universes branch off with every quantum event, or whether the universe is fundamentally unknowable. So hit that like button and subscribe, because what you're about to discover will challenge everything you thought you knew about existence. In 2025, researchers surveyed quantum physicists about what quantum mechanics actually tells us about reality, and the results were shocking, with 36% believing the mathematical wave function represents something physically real, 47% viewing it merely as a useful calculating tool, and the remaining scientists holding wildly different views, revealing that the people who understand quantum mechanics best are the most divided about what it means. And this disagreement isn't about minor details, but about the fundamental nature of reality itself, raising a question that keeps physicists awake at night. If the experts can't agree after 100 years of studying this, what does that say about the nature of the universe we inhabit? Quantum mechanics exhibits non-locality, meaning when you measure one particle in an entangled pair whose partner is miles away, the measurement seems to rip through the intervening space to instantaneously affect its partner, a phenomenon Einstein famously called spooky action at a distance. And recent experiments have confirmed this isn't just theoretical, but demonstrates that quantum effects persist across macroscopic distances of hundreds of miles, with MIT physicists discovering that neutrinos traveling 450 miles at close to light speed maintain quantum superposition without individual identities, proving we cannot escape quantum mechanical descriptions even when particles traverse distances longer than most family road trips. The implications are staggering because if fundamental particles don't have definite properties until measured, and if measuring one particle instantly affects another across vast distances, then either information travels faster than light, violating Einstein's relativity, or reality itself is fundamentally non-local, meaning the universe is interconnected in ways that defy our intuition about separate, independent objects existing in space. But the weirdness extends far beyond non-locality into something even stranger called contextuality, where properties of particles exist only within the context of measurement, like words in language whose meanings change depending on context. And physicists now consider contextuality more of a hallmark feature of quantum systems than non-locality, because a single particle is a quantum system in which you cannot even think about non-locality since the particle is only in one location. Physicists John Stuart Bell, Simon Cauchin, and Ernst Specker proved in the late 1960s that quantum systems cannot possibly have hidden variables defining the values of all their properties in all contexts, meaning before measurement. A particle doesn't secretly know what result every possible measurement will yield. It genuinely doesn't have those properties at all until the measurement forces reality to choose, and this strikes at the heart of our assumptions about objective reality existing independent of observation. The classic example involves firing photons at two parallel slits in a barrier where those passing through one slit interfere with those going through the other. Their wavy ripples either boosting or canceling each other, yet measuring which slit a particle goes through invariably indicates it goes through only one. But then the wave-like interference vanishes, meaning the very act of measurement seems to collapse the superposition, creating what physicists call the measurement problem. For decades, researchers stalled at this impasse because they cannot say exactly what a superposition is without looking at it, but if they try to look at it, it disappears. And one potential solution, developed by Israeli physicist Yakir Aharonov and his collaborators, suggests a way to deduce something about quantum particles before measuring them by using the two-state vector formalism, which postulates quantum events are in some sense determined by quantum states not just in the past but also in the future, meaning causes can seem to propagate backward in time, a phenomenon called retrocausation that challenges our linear understanding of cause and effect. Researchers in Israel and Japan proposed experiments using this framework to sneak a glance at where a photon actually resides when placed in superposition. And they predict the answer will be even stranger than two places at once. Because although the traditional view of superposition might seem odd enough, it's possible a superposition is a collection of states that are even crazier, with quantum mechanics just telling you about their average, meaning the reality underlying quantum phenomena might be far weirder than anything we've imagined. The measurement problem becomes even more troubling when we ask what constitutes an observer or measurement, because according to the Copenhagen interpretation, the collapse of the wave function takes place when a conscious observer is involved. But physicist Roger Penrose suggested the opposite, that instead of consciousness causing collapse, wave functions collapse spontaneously, and in the process give rise to consciousness. A hypothesis so strange that when experimental results suggested such processes might occur within microtubules in the brain, it raised the possibility that consciousness is a fundamental feature of reality, arising first in primitive biostructures. Eugene Wigner, who originally promoted the idea that consciousness causes wave function collapse in the 1960s, later rejected his own interpretation in the 1970s and 1980s, admitting in remarkable candor that physicists probably go beyond their competence when searching for philosophical truth. Yet this hasn't stopped the debate because we still don't know what triggers the transition from quantum superposition to classical reality, whether it requires human consciousness, any measuring device, or happens through some objective physical process we haven't discovered. The puzzle deepens when we consider quantum decoherence, the process explaining why macroscopic objects don't exhibit quantum superpositions despite being made of quantum particles, because decoherence represents an extremely fast process for macroscopic objects, since these are interacting with many microscopic objects with an enormous number of degrees of freedom, and the time taken for off-diagonal components of the density matrix to effectively vanish is called the decoherence time, which is typically extremely short for everyday macro-scale processes. When a quantum system interacts with its environment, information about its state leaks into surrounding particles, electromagnetic fields, and measurement devices, disrupting the delicate phase relationships between quantum states and causing the system to behave classically. Yet here's the critical point that troubles physicists. Decoherence does not generate actual wave function collapse. It only provides a framework for apparent collapse because components of the wave function are decoupled from a coherent system and acquire phases from their immediate surroundings, while a total superposition of the global wave function still exists at some level. This means decoherence explains why we don't observe superpositions of measurement results, but doesn't explain why we observe measurement results in the first place, leaving the fundamental question unanswered and forcing physicists to grapple with interpretations that seem increasingly divorced from common sense. In photosynthesis, plant cells collect light particles, which release energy-gathering particles called excitons that carry energy to the reaction center, where it's turned into chemical energy, everything happening in a billionth of a second to avoid losing heat with complete accuracy. And although the excitons don't travel along one single path, energy still flows instantly to the reaction center, with biophysicist Greg Engel showing in 2007 that excitons undergo quantum superposition, where particles exist in two places at once and in two states simultaneously as both particle and wave, allowing excitons to travel as a wave and feel out all possible routes to the reaction center, identifying the most efficient one to take. This discovery that quantum effects play functional roles in biological systems operating at room temperature contradicts assumptions that quantum phenomena only matter at extremely cold temperatures or microscopic scales, suggesting nature has evolved mechanisms to harness and sustain quantum coherence for biological advantage. And if quantum mechanics operates in the warm, noisy environment of living cells, then the boundary between quantum and classical worlds becomes even more blurred and mysterious. The terror that quantum reality inspires in scientists stems not just from its weirdness, but from profound disagreements about what it means, because recent surveys reveal experimental physicists favor the Copenhagen interpretation, while theorists lean toward alternatives. Yet, researchers who seem to be in the same camp didn't give the same answers to follow-up questions, suggesting inconsistent or disparate understandings of the interpretation they chose, leading to the implication that many quantum researchers simply use quantum theory without engaging deeply with what it means, the shut up and calculate approach. Some physicists, like Anton Zeilinger, argue there is no quantum world, and quantum states exist only as information in our heads describing knowledge rather than reality, while others, like Alain Aspect, who shared the 2022 Nobel Prize with Zeilinger, fundamentally disagree, insisting the wave function represents something physically real. And this division among the world's leading quantum physicists, after a century of research, reveals that quantum mechanics presents an enormous gap between successful prediction and deep understanding, unlike any other scientific theory in history. The many worlds interpretation proposed by Hugh Everett in 1957 attempts to resolve the measurement problem by suggesting reality splinters into multiple branches with each quantum measurement, one universe where you had cereal for breakfast, and another where you ate eggs, with all possibilities actually occurring in parallel universes that cannot interact. Yet critics dismiss this as ungrounded and fantastical, pointing out the lack of explanation for how or when branching happens and the unfathomably large number of unreachable worlds it implies. Carlo Rovelli's relational quantum mechanics, developed in the late 1990s, rejects any universal notion of existence, proposing that quantum systems only have properties relative to other systems that interact with them, meaning there's no absolute reality, but only relationships between observers and observed, while cubism takes an even more radical stance, suggesting quantum mechanics describes an agent's subjective beliefs about future experiences rather than objective reality. And theorists are now leaning into the discomfort, emphasizing how observers do indeed create the world they inhabit, with what's at stake being nothing less than reality itself. Recent research from the University of Southern California challenges the spooky reputation of quantum mechanics by developing a framework showing that seemingly magical correlations in quantum experiments can emerge from ordinary physical reasoning without invoking anything mysterious, suggesting quantum phenomena may not be inherently mysterious after all, with the team's goal being to expand this relationship-only framework to cover all quantum behavior, potentially bridging the gap between the physics of the very small and very large with a single unified theory. The researchers emphasize their work fully agrees with all known experimental results, so it doesn't change how current technologies operate, but the implications could be profound because it may point toward deeper connections between quantum physics and our understanding of space and time, potentially inspiring new ideas in fundamental physics. Though whether this interpretation will gain acceptance among physicists who've spent careers working with other frameworks remains to be seen. The philosophical implications extend beyond physics into questions about determinism and free will, because superdeterminism throws out the assumption that measurement settings are chosen freely and randomly, saying there is no randomness with everything that happens from the spin of an electron to the way a physicist tweaks a dial on a detector already determined from the very beginning, written into the fabric of reality at the moment of the Big Bang, ye meaning under superdeterminism. There's no need for faster-than-light signals or bizarre temporal loops, no infinite paths or collapsing wave functions, with the strange statistical outcomes of quantum experiments all pre-programmed as the universe simply unfolds following a script written at the dawn of time. This interpretation preserves objective reality and local causation, but at the cost of eliminating genuine randomness and perhaps free will itself, leaving physicists to choose between accepting that reality fundamentally doesn't exist until observed, that infinite parallel universes branch with every quantum event, that conscious observation creates reality, or that everything is predetermined from the beginning, none of which align with our everyday intuitions about how the world works. Experiments continue pushing the boundaries of quantum weirdness, with researchers creating Schrödinger cat states involving many atoms, where macro-scale superpositions help explore the transition between quantum and classical worlds. Yet MIT physicists found neutrinos traveling over 450 miles, were statistically most likely to be in a state of superposition with no definite flavor or identity, with the data being in high tension with classical descriptions of how matter should behave, making it statistically unlikely the data could be explained by any model where objects always embody definite properties, rather than exist in superpositions. These experiments demonstrate we cannot stop using quantum mechanics even when describing processes happening over large distances in the big world we live in, rather than just the strange microscopic quantum realm. And physicist David Kaiser notes that while many people think of quantum mechanics applying on small scales, what's breathtaking is that we can't escape quantum mechanical descriptions even when things travel hundreds of miles, fundamentally challenging our intuitions about the classical macroscopic world emerging cleanly from quantum foundations. Perhaps most unsettling is that physicists have designed no experiment capable of distinguishing between major quantum interpretations, meaning, starting in the 1970s, some of the most bizarre implications of quantum theory, most prominently the spooky phenomenon of entanglement, have been verified by precise experiments, yet we have no clue how any of the fundamental facts of quantum mechanics, including wave-particle duality, entanglement, quantum tunneling, or the double-slit experiment actually work, with the quantum world continuing to be a fairyland defying common sense where anything can happen. Last year's Nobel Prize was awarded partly for using these strange properties to trap ions and atoms for quantum computing applications, demonstrating that despite not understanding what quantum mechanics means, we can harness its principles for revolutionary technologies. But this pragmatic success doesn't resolve the deeper mystery of what quantum theory tells us about the nature of reality, leaving physicists in the uncomfortable position of using their most successful theory without agreeing on what it means. The crisis extends to emergence, the phenomenon where complex behaviors arise from simpler components, because physics has failed to explain this central and deep mechanism in the workings of the natural world. And in fact, physics cannot explain emergence even in its own narrow domain, for instance, in the field of superconductivity, with physicists unable to make the logical leap from the behavior of a quark to the behavior of a strand of DNA composed of multitudes of quarks. Understanding emergent behavior may be the single most important goal for physicists wanting to understand how physics connects to other sciences and the human world. Yet the quantum foundations remain so mysterious that building this bridge seems impossible, leaving us with a theory that perfectly predicts experimental outcomes to extraordinary precision while offering no coherent picture of the reality producing those outcomes. A situation unique in the history of science and profoundly troubling to those seeking genuine understanding rather than mere calculation. What makes quantum reality truly scary for scientists isn't just its counterintuitive nature, but the possibility that the community is split on whether there is a boundary between the quantum and classical worlds, with 45% of respondents saying yes, 45% no, and 10% unsure, meaning physicists cannot agree on whether quantum mechanics applies everywhere or only at small scales, whether consciousness plays any role in measurements, or whether the wave function represents objective reality or subjective knowledge. And these aren't abstract philosophical debates, but fundamental questions about the nature of existence that remain unresolved after a century of intensive research. The discomfort grows when considering that younger physicists and PhD students vote for radical interpretations like many worlds and relational quantum mechanics at higher rates than senior scientists, suggesting either that fresh perspectives are needed to solve these problems or that experience with quantum mechanics breeds justified skepticism about bold interpretations. But either way, the field shows no signs of converging toward consensus, leaving us in the strange position of building quantum computers and quantum sensors while lacking agreement on what quantum theory actually describes. Some physicists, like Steven Weinberg, have stated it's a bad sign that those who are happy about quantum mechanics and see nothing wrong with it don't agree with each other about what it means, highlighting that the problem isn't just that quantum mechanics is weird, but that its defenders cannot present a unified account of that weirdness, fragmenting into incompatible camps that might agree on predictions but fundamentally disagree on ontology. The situation has led philosopher Tim Maudlin to criticize the Copenhagen interpretation's approach that physicists should focus on calculations rather than understanding, arguing there exist interpretations offering detailed explanations of how the world functions, yet scrutiny of these alternatives reinforces skepticism as they appear convoluted and implausible to many scientists, leaving us in a state where shutting up and calculating seems like the only practical approach, despite being intellectually unsatisfying to those who entered physics to understand reality, rather than merely predict experimental outcomes. Recent experiments have closed loopholes that might have explained quantum correlations through local hidden variables, with researchers in China designing elaborate setups involving mirrors, lasers, crystals, splitters, and plates, combined with random number generators to observe Hardy's paradox without the variables that compromised past experiments, and their results reinforce the growing consensus that local realism is not sufficient to explain quantum phenomena, meaning either locality or realism must be abandoned, forcing us to accept that either objects don't have definite properties before measurement or influences propagate faster than light, neither option compatible with our everyday understanding of reality. The 2022 Nobel Prize in Physics honored scientists who used entangled photons to overthrow reality as we know it, according to Scientific American. Yet, this overthrowing of reality hasn't led to a new consensus about what replaces it. Only deeper appreciation for how profoundly quantum mechanics challenges assumptions we thought were bedrock truths about the universe. The mystery persists, partly because asking about the underlying nature of reality assumes it follows rules fitting our intuition, but the opposite may be true, with our perception of reality limited by senses and capabilities, while the true rules governing the universe might be more foreign than we can imagine, and we talk of particles occupying points in space when they're actually energetic spikes or excitations in underlying quantum fields permeating the entire universe. Fields are considered more fundamental than particles because the mathematics doesn't work without them, yet the quantum nature of a field means it can't be observed directly, since any observation requires energy forcing the field to produce a particle, creating a situation where we can only observe the manifestations of reality rather than reality itself, leaving physicists to wonder whether there exists an objective observer-independent reality, or whether reality is fundamentally intertwined with measurement, observation, and interaction at the deepest level. This quantum reality scares scientists because it undermines the foundational assumption that drove the scientific revolution: the belief that nature operates according to laws we can discover through observation and experimentation, independent of our presence. Yet quantum mechanics suggests this independence might be illusory, with the observer playing an inextricable role in determining what is observed. Until physicists devise experiments distinguishing between interpretations beyond those requiring local realism, which have been ruled out, that choosing between interpretations remains a matter of aesthetics and philosophical preference rather than empirical science, leaving us philosophizing superficially instead of relying on scientific intervention. And physicist Renato Renner stresses there is nothing wrong with just doing calculations, noting we wouldn't have quantum computers if everyone focused on foundations rather than applications. Yet this pragmatic approach leaves unresolved the deepest questions about existence that drew many people to physics in the first place. The journey into quantum reality reveals a universe far stranger than our rudimentary perceptions suggest, with evidence gathered from everyday sensory experience, yielding clouded conceptions of our world. And assessing existence, while failing to embrace insights from modern physics, would be like wrestling in the dark with an unknown opponent. Yet, embracing those insights forces us to abandon cherished beliefs about objective reality, determinism, and the separation between observer and observed. Quantum physics captivates because it defies everyday experiences, with matter behaving as both waves and particles, the universe composed of indivisible quanta, our ability to predict only probabilities rather than specific outcomes, and its non-local operation in both space and time, with effects most apparent on smallest scales, making it one of the most peculiar discoveries about the universe. But we often incorporate ourselves into the equation, introducing concepts like observation, measurement, and interaction that might say more about us than about the reality we're trying to understand. Physics cannot explain why the universe works as it does, only elucidate how it functions, and to understand the fundamental nature of reality, we must ask the universe questions about itself and heed its responses, accepting that anything else we add is our own construct. Not the universe's, yet the responses we receive from quantum experiments are so bizarre, so contradictory to our intuitions, and so open to multiple interpretations that scientists remain divided on what those responses actually mean after 100 years of asking. The most precise and powerful theory of reality in the history of science, predicting countless experiments and spawning numerous applications from lasers to transistors to quantum computers, remains shrouded in mystery regarding its true meaning, with physicists and philosophers remaining divided over interpretation. Not because the theory fails empirically, but because its empirical success comes without clear ontological understanding, leaving us in the unprecedented position of having a theory that works perfectly while we cannot agree on what it describes. And this fundamental mystery at the heart of our deepest understanding of nature is what truly scares scientists, because it suggests reality might be fundamentally unknowable in the way we hoped to know it when the scientific method was first developed centuries ago to reveal nature's secrets.